Chapter 10, Group Homomorphisms. Homomorphism phi from a group G to a group G bar is a mapping from G to G bar that preserves the group operations. That is, phi of AB is equal to phi of A, phi of B for all A and B in G. Here we use multiplicative notation, and the first operation is the operation of G, which is summative. The second operation here is the operation of G bar, which is summative again. The kernel of a group homomorphism phi from G to G bar is the set X in G such that phi of X is E, where E is the identity of G. And this is how the kernel is denoted. Example 1. Any isomorphism is a homomorphism that is also onto and one-to-one. A kernel of an isomorphism is the trivial subgroup consisting only of the unity of the group G. Example 2. Here Ch10 is the general linear group. It consists of all 2 by 2 matrices with entries from the real numbers, and each matrix has determinant different from 0. Let R star be the group of non-zero real numbers under multiplication. Then the determinant mapping, the matrix A is mapped to its determinant, is a homomorphism from Ch10 to R star. The kernel of the determinant mapping is the special linear group. It consists of all 2 by 2 matrices with determinant equal to 1. This is a group homomorphism because the determinant of a product of 2 matrices is equal to the product of their determinants, a property that we know from linear algebra. Example 3. The mapping phi from R star to R star defined by phi of X equals the absolute value of X is a homomorphism with kernel -1, 1, the set of these two numbers. This follows from the fact that the absolute value of a product is a product of the absolute values of the numbers. Example 4. Let Rx denote the group of all polynomials with real coefficients under addition. For any f polynomial from this group, let f prime denote the derivative of f, the way it is defined in Calc 1. Then the mapping f goes to f prime is a homomorphism from this group to itself. The kernel of the derivative mapping is the set of all constant polynomials, and it is a homomorphism because the derivative of a sum of 2 polynomials f and g is f prime plus g prime, a fact that we know from Calc 1. Example 5. The mapping phi from Z to Zn, defined by phi of n equals m mod n, is a homomorphism. The kernel of the mapping is the set of all multiples of n. It is the cyclic subgroup generated by n. Example 6. The mapping 5x equals x squared from R star, the non-zero real numbers under multiplication, to itself is a group homomorphism, since 5ab is a plus b squared, which is a squared plus b squared for real numbers, a and b, and this is 5a, 5b. The kernel is the set of these two real numbers, 1 and -1. Example 7. The mapping 5x equals x squared from R, the real numbers under addition, to itself is not a homomorphism, since the image of a sum of a plus b is a plus b squared, which is a squared plus 2ab plus b squared, whereas 5a plus 5b is only a squared plus b squared. When defining a homomorphism from a group in which there are several ways of representing elements, caution must be exercised to ensure that the correspondence is a function. The term well-defined is often used in this context. For example, since 3x plus y is 3x plus 3y in Z6, one might believe that the correspondence x plus 3, this is the coset in Z factored by the group generated by 3 to Z6 homomorphism, but it is not a function, because 0 plus the subgroup is equal to 3 plus the subgroup in the factor group, because 3 is 0, not 3. But 3 times 0 is different from 3 times 3 in Z6. Here, to the left we have 0 in Z6, to the right we have 9 mod 6, which is 3 in Z6. Theorem 10.1. Let phi be a homomorphism from a group G to a group G bar, and let G be an element of G. Then, first, phi carries the identity of G to the identity of G bar. Second, phi of G to the n is phi of G all day to the power n for all integers n. Third, if the order of G is finite, then phi of G has order that divides the order of G. 4. The kernel of phi is a subgroup of G. 5. Phi of A is equal to phi of B if and only if these two cosets are equal. And 6. Phi of G is G prime. If phi of G is G prime, then the preimage of G prime, which is by definition the set of all x in G whose image phi of x is equal to G prime. So this set is just the coset of the kernel that contains G. G times the kernel. The proof of the first two properties is the same as the proof of the corresponding theorem for group isomorphisms. To prove property 3, let's n be the order of G, then G to the n is equal to the unity of the group, then E is the unity of G bar. It is denoted the same way. It is equal to as the unity of G. It is equal to phi of E. Because of this equality here, this is phi of G to the n, which is phi of G all that to the n, according to property 2. Then the order of phi of G must divide n, as we know, but n is the order of G, so this proves property 3. To prove property 4, we use the one-step subgroup test. The subset is the kernel of phi. It is not empty because the unity of G is in the kernel of phi, according to property 1. So let A and B be any two elements in the kernel. We must show that AB to the negative 1 is also in the kernel. Since phi of A is C and phi of B is C, and those are in the kernel of phi, phi of A B to the negative 1 is this, because phi is a homomorphism. The inverse of phi of B to the negative 1 is phi of B to the negative 1, and this is E times E to the negative 1, which is C. Because the image of this product is C, this product is in the kernel. And this completes the proof. The one-step subgroup test guarantees that the kernel is a subgroup. To prove property 5, we observe that phi of A is equal to phi of B for some elements A and B and G, if and only if phi of B to the negative 1A is equal to E, as one can see here. If and only if B to the negative 1A is in the kernel, and this is true if and only if these two cosets are equal. So this completes the proof. To prove property 6, we have to prove this equality, and we prove it as we prove equality of sets, two opposite inclusions. First, let X be an element of the left-hand side. This means that phi of X is G prime, but phi of G is also G prime, so phi of G is equal to phi of X. Then by property 5, these two cosets are equal, which means that X belongs to this coset, but they are equal, so it belongs to this coset also. And we prove the first inclusion. To complete the proof, we must prove the opposite inclusion, and it is this one. Suppose that K belongs to the kernel of phi, then phi of gk is phi of g phi of k, phi of g is g prime from property 6, phi of k is c, because k is in the kernel of phi, and this is g prime. Thus, by definition of this set, gk belongs to it, and this proves the inclusion, the opposite inclusion, and it completes the proof of the property 6. Theorem 10.2, properties of subgroups and homomorphisms. Let phi be a homomorphism from a group G to a group G bar, and let H be a subgroup of G. Then phi of H is the set of all images for elements from H, and this subset of G bar is a subgroup of G bar. It is a subgroup of G goes to a subgroup of G bar. If H is cyclic, then phi of H is cyclic. If H is abelian, then phi of H is abelian. If H is normal in G, then phi of H is normal in phi of G. Phi of G may be a subgroup, proper subgroup of G bar. So phi of H may be not normal in G bar, but it is normal in phi of G. If the kernel has order n, then phi is n to 1 map from G to phi of G. If the kernel, if H has order n, then phi of H divides n. If K bar is a subgroup of G bar, then the preimage of K bar is a subgroup of G. If K bar is a normal subgroup of G bar, then the preimage of K bar is a normal subgroup of G. If phi is on 2, and the kernel of phi is E, the trivial subgroup of G, then phi is an isomorphism from G to G bar. We'll skip the proof of these properties, but each of them is easy to prove, as you can see. The special case of property 8 of theorem 10.2, where K bar is the trivial group consisting of the unity of the group G only, is important, and it is actually the content of this corollary. Let phi be a group homomorphism from G to G bar, then the kernel of phi is a normal subgroup of G. Example 8. Consider the mapping phi from C star to C star. This is the group of all non-zero complex numbers under multiplication. And phi is defined by phi of x equal x to the fourth. Since xy to the fourth is x to the fourth, y to the fourth, for any two complex, non-zero complex numbers, we conclude that phi is a homomorphism. Clearly, the kernel consists of all complex numbers x such that x to the 4 is 1. And there are 4 such complex numbers whose fourth power is 1. 1, negative 1, I, and negative I. So by property 5 of the theorem, we know that phi is 4 to 1 map. And let's find the elements that map to 2. Since phi of 4th root of 2 is 2, then by property 6, the set of all elements that map to 2 under phi is the coset of the kernel that contains 4th root of 2. And this is just this set. You multiply each number from the kernel by 4th root of 2, and you end up with this coset. So these are all the numbers that map to 2 under phi. Example 9. Define phi, a map from Z12 to Z12 by phi of x equals 3x. In Z12, this is the same group. The operation is addition mod 12. So this homomorphism, because 3 times a plus b is equal to 3a plus 3b, because we reduce mod 12 on both sides. The kernel of phi consists of these 3 numbers, 0, 4, and 8. Because we have 3 elements in the kernel, we know from property 5 of theorem 2 that 5 is a 3 to 1 mapping. Since phi of 2 is 6, we have by property 6 of theorem 1 that the inverse image of 6 is 2 plus the kernel of phi. 2 plus 0 is 2, 2 plus 4 is 6, 2 plus 8 is 10. Also, the cyclic group generated by 2 is his image, that is phi of 2 is 6, phi of 2 times 2 is 6 plus 6. Mod 12 it is 0, so any multiple of 2 is either 0, is mapped in either 0 or 6. And this group is also cyclic. It is the group generated by 6 in Z12. The order of 2 is 6, and the order of phi of 2, which is the order of 6, is 2. And the order of phi of 2 divides the order of 2. And 2 divides 6, in agreement with property 3 of theorem 1. If K bar is 0, 6, then the pullback of K bar is this set, any number that maps to 0 or 6 under 5. And this is just what property 7 of theorem 10.2 says. The pullback must be a subgroup of Z12, and it is a subgroup generated by 2. Theorem 3, the first isomorphism theorem. Let phi be a group homomorphism from G to G bar, then the mapping from the factor group of G by the kernel of phi to phi of G, given by coset G times the kernel of phi goes to phi of G, is an isomorphism of groups. Symbolically, G factored by the kernel of phi is isomorphic to phi of G. Proof. Let us use psi to denote this correspondence. The coset of the kernel with representative G, G is an element of the group G, goes to phi of G. Phi is well defined, that is, the correspondence is independent of the particular coset representatives chosen, because of property 5 of theorem 1. Phi of A is equal to phi of B if and only if A times the kernel of phi is equal to B times the kernel of phi. And it is also one-to-one. Psi is also one-to-one. To show this psi is operation preserving, we start with psi of the product of two cosets of the kernel, one containing x, one containing y. Here x and y are elements of G. Then we first multiply the cosets. It is the coset with representative xy. Then psi of this coset is just phi of xy, but phi is a homomorphism of groups, so phi of xy is phi of x, phi of y. Psi of x times the kernel of phi is just phi of x, and psi y times the kernel of phi is just phi of y. So we have psi of the product of the coset is equal to psi of the first coset times psi of the second coset. And this is this completes the proof of the first isomorphism theorem. Corollary. If phi is a homomorphism from a finite group G to a finite group G bar, then the order of the image phi of G divides the order of G and also divides the order of G bar. The order, we know that phi of G is a subgroup of G bar, and the order of a subgroup divides the order of the group. this way. The order of phi of g divides the order of g bar, and the order of phi of g divides the order of g because of the first isomorphism theorem. The order of phi of g is equal to the order of the factor group of g by the kernel of phi, and it is the divisor of the order of g. Let's consider the additive group R, the real numbers under addition, and the group of all complex numbers with absolute value 1 under multiplication. The map W that sends a real number x to cosine of x plus sine of x is a group homomorphism because we have this equality, a fact that we know from trigonometry. This can be checked easily with trigonometric identities. This means that we have a group homomorphism, and the kernel of this group homomorphism is the set of all integer multiples of 2 pi, because sine and cosine are periodic with period 2 pi. Hence, the real numbers under addition, this group factored by the subgroup generated by 2 pi, is isomorphic to the circle group